Hello friends, welcome back to another session of the Raytracer challenge by James Buck. In this YouTube video series I am going to implement a Raytracer based on the book shown here in Rust, a language I'm learning while doing this. So we are learning together doing Rust and implementing a Raytracer. Two things which are quite fun. So you can follow along easily by either checking out these videos or this series or by taking a look at GitHub, where all the code which is produced here is pushed after the sessions are done, and you can actually download them and build them for yourself to have fun and play around with this code. All the needed links and descriptions are down below in the text to this video. So thanks for joining me again, and if you like this video, please give it a thumbs up. It really helps me getting more people to see this and to get a better feedback of if you like it or not. Please leave comments if you want to give me some annotation or information on what you liked especially, or what I should do next, or if you have any questions, please feel free to ask them as others have already done. So, okay, let's get going now. The last thing we actually did was taking a look at writing a world struct. So let's take a look what we did here. We actually created some sort of world structure which holds an arbitrary amount of bodies. Bodies are three-dimensional objects in our world, like a sphere, for example, or like anything else you might have there. And we have an arbitrary amount of lights, which in our case are only point lights currently. So only lights which are going from one point, irradiating light into every direction. We might have spotlights and stuff like that later on, but we will see. For now, we only have point lights. That's why we are only holding a vector of point lights here. Our world has actually two different functions we implemented the last time. The first one is a way of intersecting a world with a ray. So we can check if we are firing a ray from our Raytracer into the scene, into the world. We will get back a list or a collection of intersections we implemented, and we can then handle those intersections and calculate further things with them. Like, for example, the color which the ray should have at this position if it's projected through a canvas. And this is exactly the second function we have here. We are calculating based on the ray, on a given ray, we are calculating which color the pixel on the canvas where we are going through should actually have. And we are using our implemented Phong lighting for this and calculating based on this material the lighting and then returning the color. We have created tests for this as well, as you can see here, and it's always a good idea before starting something new to ensure that all our tests are still running. So let's quickly compile this stuff and check that all the tests are still running. And as you can see, all our tests are still good and okay, and everything is fine. So we have a clean state where we can now start going further along. Okay, so what are we up to next? We will implement a way of looking at the scene from a specific position. At the moment, if we are ray tracing things, like for example this sphere, which we have ray traced last time, something like this here, we are always looking at it from a defined position. So we are always looking at it from something like the one we are providing here in our binaries, like chapter 6, where we're rendering this sphere. We are always actually defining from where our rays are coming. Where is those basic definition here? So we have a specific ray origin, which in our case is simply -5 into the z-axis, and we have positioned the virtual canvas where we are shooting those rays through to get a rasterized image, so to say, at a specific z distance, and we are giving it a size and something like this. So we are always looking at this thing from the original coordinates space. So here's our sphere somewhere, and we are just into the scene somewhere here, but we are not really moving along the different axes, or we couldn't easily say, okay, we want to look at this sphere from here, or from here, or from here, or from here, or from anywhere actually. So that's something we want to do. We have now a world which could hold multiple objects, like multiple spheres at the moment, because we haven't implemented anything else than a sphere yet. But we want to be able to take a look at this one from different positions. And in order to do that, we are going to transform, or to create some sort of transformation matrix which allows us to do exactly that. And the easiest way to think of this is like a camera object, where we have something like our eyes, or a camera, a mechanical device to do something like this. Essentially, our eyes are nothing else than a quite complex camera. So we can think of this as a camera, which we can position somewhere and look at the scene from a specific point of view. And we want to actually realize this and render this then. The only problem here is that in all our calculations, we are always transforming the objects within the scene in the world, not the position from where we look at it. Our essential position is always the same. So what we are doing here is now, or what we are going to implement, because it is much easier to do mathematically than the other way around, is we are not creating a camera which we are positioning somewhere in the world and then using this, but we are transforming the whole world inverse to where we want the camera. So let's take a look at what I am currently talking about here and what we want to achieve. Let me get out my tablet here to show some drawing, because that makes things a lot easier. So if we actually have something like, we have our coordinate space like this, and we have our sphere in the middle of this coordinate space, and we actually want to look at this thing with a camera, like for example here we have a camera which looks at this sphere. We are not actually moving this camera, but we are doing something else. We are actually, what we are going to do is we are removing this here and this there, and then let's just fill up the scene here. So what we are actually going to do is we are positioning the camera within the origin of our world, and moving the sphere, or the world, inverse to what it actually should have been with regards to the camera. Because we can easily think of this. If we have this sphere and it is in the origin of our coordinate space, and we have this camera which is in this two-dimensional diagram, it's left and to the top of this sphere. We could of course transform this camera position to the left. We could translate it to the left and up. But the other way around, we could actually transform the sphere down to the right. So if we're transforming the sphere to the right and down, the relation between the camera and the sphere is absolutely identical. And this is exactly what we are going to do here, because it makes the math we are doing there a lot easier. And so it makes things for us a lot easier. So let's take a look at how to do this and how to actually define something like a camera then. So first of all, as you might imagine, we need a camera then. So let's create a new file called camera.rs. And for our camera, the first thing we are doing is we are defining a structure called camera. And this structure is going to hold a specific amount of values. So what do we actually need to hold here? Yeah, of course, for once, we definitely need to hold the transformation matrix. However, we are in the end applying this and handling this as I've explained before, but we need to somehow handle this and to store this. So we have a matrix 4 here, and we of course need to import this, and we need to make a comma there. And okay, why is this not? So we need a V size, which is essentially the vertical size the canvas has that we are using within our camera to project all the rays through, which will be, I guess, what did we use here? It is a U size in our usual one where we had it squared. Now we will be able to define non-square canvases to render with. So I guess we can live with a U size here perfectly fine, and an H size, which is a U size value as well. So now we have this. We have the transform, the V size, and the H size. And now what we are actually going to need as well is a field of view. And a field of view is actually the angle at which our camera is kind of focusing, and the field of view will be a floating point, of course. And it's essentially, in a camera, a field of view is like the amount of image the camera is able to see. So if you have a very narrow field of view, you have kind of a very zoomed in image. And if you have a wide field of view, you have a very zoomed out kind of image. But this field of view also is reflected in how an image looks later on if you're projecting it into the two-dimensional space while you render it with a camera. You can think of a zoomed image always has another differentiation between foreground and background than actually a zoomed out image has. And this is something that we will be creating with this field of view as well. So for now, let's leave it at that. I will explain it later on when we are implementing it, how this works and what we are going to do there. So as always, the first thing we are going to do is we are creating an implementation for our camera, and we are actually defining a pubfn new, a function which is used to create the camera. And we are essentially here creating it with a V size, which is a U size, of course, an H size, which is a U size, and a field of view. And this one, of course, will return a self. So now that we have this one, we can simply create a new camera here, which has we'll take a look at the transform later on, which has a V size, it has an H size, and it has a field of view. And now we need a transform, and for the transform, we will actually take the identity matrix here. So I guess we had that here. I think that we have some sort of or was the matrix was, come on, give me the matrix. I guess the matrix had an implementation which was the creation matrix from new identity. Okay, it has an identity. That's interesting. So identity. Okay, so works out, I guess. Comparison operators cannot be changed. Yeah, I guess it works like this because it already knows it's a matrix of generic type 4. So yeah, as we are later on going to need to define this transform or override it, better said, somehow to initially put it there, we will create with transform function, which actually takes immutable self, and transform, which is a matrix 4, of course, and returns self. This is actually an interesting pattern I read about on the internet and in some places, which is quite interesting because we are not getting we are not taking a reference to self here, but essentially really we are consuming the self. So once we've done this, the original version cannot be used any longer, at least not in a sensible way. And we are simply going to do and setting this transform here now to the given transform, and then we are returning self. And what this actually does is now we can actually now do something like, when we are using it, let's see, something like we can create a camera and tell it we want a new camera with some V size and some H size and whatever inconsistent and not really useful field of view here. And then we can simply say with transform, and then we can put transform in here, and what is actually returned in the end is our configured camera object, which we can then use. And this is actually something I'm liking. I know this technique from other languages, but I've never seen it to be used for construction, where something has kind of an optional parameter. This kind of builder pattern I've seen a lot in other languages, but not used especially for this. So I like it. I will play around with it. For this use case, I guess I will use it, and then we will see how things turn out in the end. So now we have our camera. So in the following, I will quickly put some tests there, which will simply check that the implementation of our camera struct is taking the corresponding arguments, and that our new function as well as our with transform functions work as expected. So yeah, let me quickly time jump you there, and let's do this in a fast forward. So let's see if our test actually works. Let's do a cargo test camera. So has it executed the test? Running one test camera, constructing a camera. So this is working. Okay, I didn't expect anything else actually. So we are simply putting some values in here, a V size and H size, a field of view, and we are then checking that we can actually access those. And so yeah, so let's create another test. So what we are actually now testing here is that the basic transform a camera has is the identity transform. So let's quickly check that this is the case as well, and it looks quite okay. We get these warnings, but they will go away once we have finished implementing both tests work out as expected. So now let's check if our with transform function works as expected. So now we have a test here which actually uses the with transform function to create a new camera with a transformation matrix attached, which we created here by simply creating a translation matrix for testing here. And we are then asserting that not only all the fields that we have used before are set correctly, but the transformation field as well. So let's execute those tests. And the test is working as well. So our API, as we have used it here, is actually working out as we expected it to. So now that we can create a camera here, let's check what we would need to do next. Let's, in order to do this, take a look at our current rendering code, which we have here. For example, from chapter 6. What we're actually creating here is we need something like the ray origin. Yeah, we are working on that. We will take that into account with the transformation later on. We have this wall position, which actually is the canvas we are shooting the rays through to the target to get an image in the end. We have this wall size that is something we definitely need to calculate somehow. We have the field of view, that is actually how we are going to calculate this, and we have this canvas size. And then we create here a value which is called canvas pixel world size, and canvas pixel world size is actually the relation between the pixel size in our world space where our rays are shot through and the canvas size we have in pixels. And this is exactly all of those things we exactly need to combine now to calculate those canvas pixel world size. But before we are going to do that, let's take a look what we are now actually going to do by sketching something up here again. So let's think about our camera. We have somewhere here, we have our eye, And this eye, which is our camera actually, has this field of view. Yeah, so this here, this angle is our field of view. And at the end of this field of view, somewhere we have this, or let me paint it in another color. Let me do it like this. We have this, and this is our canvas, the one we are projecting lines through. And somewhere here is our scene, and we will from here we will fire rays into the scene, which will either intersect the sphere or not, and they will all go through this canvas and create a representation of their intersection there as we had before. So what we now need to calculate is actually where's this canvas gonna be, and how large it is in relation to the, we know its pixel dimensions because we are provided those information. In order to calculate the width of our canvas in world space, the thing we actually need here, based on this field of view, we can easily do by halving it. So we got a right triangle here, and now we can actually easily calculate this distance, this half of the width of our canvas here, by simply calculating the tangent of the field of view divided by 2. Now we actually have this length here, and if we actually multiplying this later on by 2, we have our full size of the canvas calculated in world space. And this is actually what we are going to do. There is one caveat. The problem here is that this only works for canvases where the width is greater than the height. We can easily calculate one based on the other because we have the relation between, we have our R, which is our H size divided by V size. So we always know the ratio between them. So if we have this value here for either the width or the height, we can calculate the other because we know the ratio they are, which has to be applied there. But the problem there is that if the vertical size is bigger than the horizontal size, so we are actually looking at a picture like this, not like this, like this, then this calculation, which we just did, is the calculation which gives us the world values for the V size. So we have to later on decide which aspect correlation we have, if it's a landscape or a portrait mode, and then calculate based on that the other value we need. So let's simply do this because it's not that hard once we know that we can use the given values, as you have seen, to calculate what we need. So we need some more values here, which we will now calculate and store once this thing is created. And I guess nevertheless this should actually be pub values. Oh no, that's the wrong place. I guess we could make those public because I want them to be accessible from the outside, I guess. And now we want to store some more variables which are kind of private to this camera, which we only need for further calculations. And this will actually be the half width, which is exactly what I've just shown here, this half calculation, either for the width or the height, in this case the width, which we will calculate out of there, which is actually a floating point because it is in world space, not in the integer canvas space, so in the rendering space. And we of course have a half height, which is a floating point, and we have an aspect ratio, which we will store as well, because why not? So in order to calculate the value here, this half value, which we don't know yet because it's based on the aspect ratio, if it's the half of the width or the half of the height, we will simply name it half size for now, and we will calculate it by actually taking the field of view and halving it and then creating the tangent out of it. So actually we are creating the tangent of the field of view half. And this is exactly what we are calculating there. And now that we have this value available, we can actually calculate the aspect ratio. And the aspect ratio is, of course, the H size, but we need to cast it into a floating point, I guess, divided by V size as a floating point. And so that we get the aspect ratio as a floating point here back. Yeah, it seems to work. So now that we have this aspect ratio, we can actually branch out here and say, okay, if this aspect ratio is bigger than or equal to 1, because we actually do not really care if it's squared. If it's a square image, the values are the same anyway. So if it's 1, then it's okay to use either branch. We are just using the first one. So if this aspect ratio is bigger than 1, this actually means that the H size is bigger than the V size. So we have a picture in portrait mode. And if we have a picture in portrait mode actually, then I can tell that the half width, come on, is actually what we've just calculated there. And the half height is actually the size we have calculated divided by the aspect ratio, because it is smaller. So we need to apply this aspect ratio to it. And now we have this value. And otherwise we have half width, which is half size. No, half height, sorry. We have the height, which is the half size. And then the half width is the half size multiplied by the aspect ratio. So now in this case we have calculated both of those values, and we should be able to simply specify them here, even though I'm not 100% sure those are defined. Now let's check. Yeah, I guess that's the problem. Aspect ratio, this one should work. Yeah, I guess this is the problem here. So let's not define them here, but let's do that in the right scope here, because otherwise the system does not know that we want them later on. So half height. And now this should actually work out. And now those values should actually be present and readily calculated. Actually, I forgot one essential part to tell you in my calculations why this actually works. You might have already assumed it if you have a knowledge of how tangents and how trigonometry works and stuff like that. I have assumed that this distance here, so the distance between our camera position or starting point where the rays are projected from to our canvas, is actually a length of 1. So this makes calculation easy, and as we can freely decide where our canvas actually is within the space for our calculations, I've just decided that it is exactly at a distance of 1. So this is actually why those calculations are so easily possible. And yeah, so now that we have all this information calculated, we can actually calculate another very important information, one which we have here, which is the canvas pixel world size. So essentially the size of our pixel in world space. So we will just call this pixel size here, and pixel size of course is a floating point. And now we can easily calculate this as well, because now we know the ratio between the real canvas and the projected canvas which we are rendering our pixels to. We can do a pixel size here, which is now simply the half width times 2, because as the name says, it is half the width and we need the full width, and we simply divide it by our real pixel size as a floating point. And in doing so, we are actually creating the ratio and therefore the size of a real pixel here in world space. So now we know what the size of any of our pixels is within our world space. And we can therefore add this information to our camera as well. Pixel size. So now that we have everything we need here in order to cast our rays through this virtual canvas, as we have done before in this case here, we now can create a new function on the camera, which we will call pubfn. Let me scroll this up here a little. Pubfn ray for pixel. And actually this, of course, needs a self-reference because we need to access our calculated information, as well as an X, which is a U size, and a Y, which is a U size, which is within our canvas domain, our pixel space. And actually, if you call it, we will return you array for, and we need to, of course, import this one for the given canvas coordinate, array which starts at the camera origin, pointing towards or through this given pixel and then into the scene. And yeah, we actually now can easily calculate this, or easily because there is this part of the transform, but we will talk about that separately in a second. So for now, let's start calculating this, and let's calculate the parts we can. We can actually take a look at our implementation before as how we implemented this. And essentially, this is the code we have to take a look at. We calculated those rays based on the world coordinate, but in order to calculate the world coordinate, we needed to take into account that the point in the middle of our canvas actually is not in the middle in the canvas space, but it is only in the world space in the middle. So we took the half of the canvas size here, and then we actually created this kind of offset here and calculated those information based on this. And essentially we are doing exactly the same here. So I guess essentially we can more or less, I guess, copy this stuff out of here and put it here and then modify it just to work for us in the way we like it to work. We of course do not need this half anymore because we have our half values obviously ready for us. So what we have here is our self half width. And now we need to take into account that our canvas isn't square anymore. So we actually have to apply the half width here, and later on in the Y coordinate section, we need to take care of half height. But here we have our half width, we have the negative of our half width, and we are actually adding the X value here. And now we need to multiply it with our pixel size, a self.pixel size. So now that we have done that, we have our world X, and our world Y is nothing more than the same thing done here. It's self half height minus Y multiplied by self dot pixel size. And now our wall point can easily be calculated. This is our world X coordinate, our world Y coordinate, and essentially the wall position Z, which was configurable before, is now minus 1.0, because as I've told you in between, which I forgot in the beginning, we have decided, or I have decided, that this distance should be 1. So we are simply moving this on the Z axis by -1, and our position of the wall is perfectly fine there and can always be there, just 1 in front of the camera. So how do we now calculate our array? We are almost finished. We only need to take into account the ray origin, which in our case is simply, as I've explained in the beginning of this session, we are always assuming that we are in the middle of our coordinate system. The camera is actually always in the middle of our coordinate system, and the world is moved around it, and we will take care of that later. It's a tuple, it's a point, and it's 0.0, 0.0, 0.0. And this is actually, yeah, let's maybe put this in its own thingy here and call it ray origin And we need to import tuple, I guess. Yeah. So we have here ray origin, and the direction will be let ray direction, our calculated point on the wall, our wall point, minus our ray origin. Therefore the direction which points from our origin to the pixel on our canvas. And of course we want to normalize this one, and this will be the direction. Oh, it was already written out here. So we have our ray direction here, and this is actually the ray we are returning. So there is a little problem with that. The problem is that even though this calculation is perfectly fine, it doesn't take into account any of the transformation information we have here. We actually have this transform here, this transformation matrix, and we somehow need to incorporate it into this calculation. Therefore, let's take a look at this now. So as we are utilizing a view transform here, which is actually a transformation of our whole world to the position where we want it and not the camera itself. So in order to actually calculate the correct position and transformation of our camera, we need to take into account our transform. And our transform is the view transform, which I've explained, that actually moves the world to the position where it would be seen from the 0, 0, 0 position instead of moving the camera itself. So what we need to do here is we need to take the inverse of this view transform, which then is the transform inverse here. We can calculate this one, and I'm just storing it here because I need it multiple times, and it actually is easier to read in my opinion than always having this inverse term there. And then we now have this inverse, which actually then is the movement of the camera in the world space. So what we now need to do is we are just moving this wall point by applying the inverse of this view transform to it, by multiplying those values, and we actually move the inverse view transform multiplied with our ray origin to move the ray origin by our inverse transpoint. And maybe we can just remove this blank line there. And so now we have actually transformed our starting point of the ray and our ray on the wall to be oriented exactly like we would like it with regards to our world view transform. So now that we have this, we are actually finished and can actually get from this camera a ray for any pixel based on our transformation. We will see how we can calculate this transformation in a more easy way, let's say, in a second, because we will create a helper which allows us to position our camera very, very intelligently and very easily in the scene in any way we want by just specifying a triple of parameters, which will then essentially specify where to actually look at in the scene, and then the rest will be calculated automatically. But first of all, let me add some more tests to ensure that our calculation we've done here is correct at all. So there we are. We have actually now 3 tests. The first one, constructing an array through the center of the canvas, which creates a canvas the size 201 by 101 and the field of view of pi by 2, so 90 degrees actually. And then we are calculating an array through exactly the center of this canvas, which is 150 actually, which is exactly the center pixel. So we are now assuming that the origin of the calculated ray should be exactly the origin of our coordinate system, and that the direction vector should point into the scene here, into the -z direction where actually our canvas lies. So this is a test without any transformation, just creating this and testing this. The next one is actually checking that array through these through the corner of the canvas, in this case pixel 0, 0, is actually calculated correctly as well. It has the correct origin point, and then it has this vector, direction vector, which should go through this canvas at the correct position. And then we have the last and most complex test, which checks that array can be properly constructed when the camera is transformed actually. So we are creating a new camera here, and then we are creating a rotation around the y-axis and a translation, and we are first translating this one by 0, 0, -2 and 5.0 pixels, so by 0, -2 and 5, and then we are rotating it by pi divided by 4, and then we are creating an array for the pixel which is actually here the 0, 0 position, and then we are asserting that the origin point is correct, which is the translated then, of course, because the camera has been moved, and that we are actually pointing into the right direction based on those rotation calculations. So let's see if our camera tests are running here. And yeah, they are not. Okay, so let's see what we did wrong here. Okay, in order to be able to better read this, because I think I've done something wrong with these values here. Let's split those into a little bit different calculations. What have I actually done there which I shouldn't have done? Let's see. So let's call it offset x is x as f64 multiplied by self pixel size, and let offset y as f64 multiplied by pixel size. And now we can remove this and just have an offset x there and an offset y there. So now we have this calculation here, which is essentially what was there before, which calculates the offset position from the x and y of the position, I guess, of the canvas. And as we are looking at -1, we need to, we need to subtract this here from the width and from the height. So we are moving into the correct position, I guess. Let me think. Yeah, we are starting on the right side now and going this way. And yeah, exactly. We are, when the x is getting bigger, we are subtracting more. And when the y is getting bigger, we are subtracting more. So we are actually starting here and then going into this direction. Okay, yeah, this is actually correct. Should be correct. Okay, let's see again what is actually what are the values now failing there after we have changed things. So we would expect, actually this one seems to be the direction. So in our first test we expect the direction to be plainly looking at 0, 0 and -1, and it's off by a fraction of, it's actually only off by a fraction. Could it be the problem that we are actually not offsetting here? So we are not actually projecting the ray exactly to the midpoint of our pixel. It shouldn't be a problem in the later on calculation, but it may be a problem by not 100% being in the middle now, but a little bit off because we are in the top left corner of our pixels. So what would happen if I did something like put a 0.5 here and a 0.5 on this pixel to simply ensure that the calculation we are creating there is exactly in the middle of the pixel. Let's see. Okay, now we have one failing test. Okay, so now the transform is broken. So I guess this was the problem here. And now we have this transform which is still broken, but how is it broken? It's quite off. So what is actually off there? See, the transformation test is here. So it is not the origin that is actually off here, it is the direction as well. But why is it so off? So we are creating matrix, translation, ray for pick. Wait a second, ray for pixel 0, 0. I think I copied this one from the test before, but I guess it should have been 150, just to the middle of the camera. Let's check. Yes. Okay, finally. So now this is working as expected, and yeah, we have a camera implementation which actually can calculate proper rays for us in a way that we want and need them. But yeah, before we can actually do something really useful with it, we need a way to specify this camera transform in a more easy way. So it would be quite nice if we had a better way of specifying this transformation. And it would be quite nice because I would like to be able to specify a position where the camera actually is and where it is looking at, and maybe in which rotation it is looking at this. So here's our target, here's our camera position, and we need to see how it is rotated in space. So we need the camera position, we need the target position where it is pointing at, and we need this rotation. So actually we need to know where up from the camera is. And this is actually the default way to usually implement this, is by creating some sort of function. Let's call it look at from position. And it's actually the same build-up pattern we used before. We will be returning a self here, and we will take in a mutable self because we will be modifying the transformation. And yeah, the first thing then is we are getting the from, the position actually. We are then getting the to, so where actually is this camera pointing to. And then we will get another vector which describes where up from the camera is, so to actually describe this rotation. So this should be quite easily doable to get this information in here. So we have this tuple. So now we need to, let's format this. Okay, I punched the wrong key combination, though there it is. Let's format this. So now we can actually fill this with a little bit of life. So in order to create this, we need to think about some things here, but it is essentially quite easy. First of all, we need to calculate some more information from the one we already have. So the first of all, we need to calculate a forward vector, which actually can easily be calculated by simply taking our target and abstracting the origin from there, and we have the vector which actually points into the correct direction, and then we are, of course, as always, normalizing this result to make sure it has a length of 1. So now we have our forward vector, which is actually pointing into the direction to our target. So now that we have this, we can actually calculate the left vector. And even though it might not be clear yet why we need this one, let's assume we want this one, which is actually quite easily be calculated as well, as it is the cross product from the forward and the up vector. So the cross product of those two vectors, we have the up one and the forward one, should be the one pointing on the other axis, as those are all then perpendicular to each other. So we are calculating this one. So now that we have this one, we can actually help ourselves a little bit. When we are using this system, we usually do not want to always specify the exact up vector, which is into the correct orientation perfectly with regards to the orientation of the camera. So we could do all sorts of quaternion magic there for rotating the camera instead, but usually you get it at up vector. And what we are doing now is we are ensuring that we only need approximate up vector, that it doesn't need to be 100% specific. And that is essentially what we are using the left vector for, because now when we are creating the cross product between the left and the forward vector, we can actually use this information to create the real up vector, which is then an approximation of all of this, and it usually works out quite well. So let's do this. Let's do true up equals left cross forward. And once we have all of those vectors created, we can actually use the information from them to create a transformation matrix, which does exactly what we want it to do. So let's go ahead and do this and create our orientation transform, which would be a matrix, and it would be filled with the following informations. So this is actually our orientation transform, which rotates the camera into the correct position based on the left, our left vector, our new calculated up vector, and our forward vector. So we are using those informations from all of the three axes to create a transformation matrix, which actually applies this information to the coordinate system we are putting it on. So if we put a vector in there, it will be transformed into this new coordinate space that we have created by defining this three-dimensional cube. And essentially, it is quite easy to understand if you think about what a matrix multiplication does with all the components. And if you do this on the x-axis, so the left vector, and the y-axis, so the up vector, and the z-axis, so the forward vector, accordingly to this matrix, it is quite easy to see why this actually transforms it into the proper coordinate system. So just think about how matrix multiplication works in this case, and it is quite easy to see why this works, because we are essentially really creating this three-dimensional vector space there and transforming it accordingly. The only thing missing now actually is, it is actually the origin, so this from position that we have here, because we haven't really incorporated this, because we need to start our vectors at this position. So we need to move them there first, and then we need to manipulate their orientation. So in order to do this, we can simply create another matrix, the translation transform, which is actually a translation matrix then, and it is moving this thing in the reverse, so from the position it was given, so that we are actually transforming it to the right position in the end. So let's do this here, and let's do from x minus from y and minus from z. And now our self-transform is actually nothing else than the orientation transform multiplied by our translation transform. And now we can return self here. And the reason why we are moving here, why we are moving here into the wrong direction is that we are actually creating a transformation which transforms the world and not the camera itself. So the camera position itself needs to be in the reverse position than it was specified, because if the camera is here, we are not actually moving the camera from this position to this position, but we are moving the world from this position to this position and leaving the camera in the center actually. So yeah, that is essentially what we are doing there. And this is why those are negative values here. So now we have look at from position, and we can actually quite easily specify now where our camera should be positioned and where it should look. So maybe we should quickly create some tests for this and then wrap things up and do something with all the things we have implemented. So now we have 4 more tests, actually one which checks that the transformation is for a default orientation is the identity matrix, which essentially is that if we are in the center of the system here, if the 2 vector is pointing into -z direction, this is essentially where we are starting out at. And the up vector is just on the y up, so we are actually in the center and just looking into -z direction. Then the transform matrix should be the identity matrix if we are looking at this position. If we are looking into positive z direction, then we should actually, which is indicated here, that we are looking into positive z direction, then the transformation matrix should actually scale the x and the z values, so by -1, so just looking into the other direction and looking into the other x direction there, which would be quite right. And then we are ensuring that actually this transformation moves the world and not the camera itself, by just making sure that if we have another orientation here and we are looking at the center of our coordinate system and just normally up, that essentially the translation here is into the negative direction, so it is the other way around. But what I don't actually see here is, I guess I've made an error here. There should be a 0. Oops, there should be a 0 because we don't have a translation on one of the other axes. Yeah, and then there is the most complex test, which is just more or less an arbitrary looking at. So we have a from, which is somewhere in our world, we have a to, which is somewhere in our world, and we have an up, which is something like in the x and y direction, so somewhere in this direction. And the camera is rotated around quite a bunch, and so we are just checking that the transformation here is what we expect it to be. So yeah, let's see if now the tests in this situation are running, or if we are getting failures like the last time. I hope they are running. Oh no, of course they are not. Let's take a look at our function here, which we have created. Today we have some problems, but yeah, so it's a good thing we are writing tests for this. So no, not ray for pixel. Look at from position. So let's see if we did everything right there. Oh, and yeah, of course we did not, because we need this values to be negative as well, because they are actually presenting the same issue. We need to have this forward into the other direction as we are moving the world and not the camera itself. So this might already be our problem there. We have this correct here. So yeah, let's maybe just run the tests again and let's see. And okay, now 1 is failing. So essentially this is working, but our arbitrary view transformation is panicking somewhere, and maybe it is just that I've entered some wrong data there. Okay, it's a completely different transform that we are getting out of this. So maybe let's quickly check what we have done there. It might be that we did forget to normalize something here. So our forward vector is normalized. Then we have a left with a forward cross. Oh, okay, we did not normalize the up vector, and this one might be. Let's just check if this already corrects the problem. And it does. Yeah, we just forgot to normalize the up vector, because in all of the tests before, let me quickly scroll there. So in those tests here, the up vector was already normalized, so it had a length of 1 here as well, but in this one it did not. So we needed to normalize this then in order to have all our calculations to be correct. Otherwise we would have somehow integrated a scaling into our calculations, and this obviously screwed something up. So yeah, now we actually have fully implemented a camera which we can create and which we can then essentially use. So I guess we now have implemented this. So yeah, let's clean up those files here a little bit. And then let's create, I guess, by copying this chapter here, chapter 6, let's create a new one and call it chapter 7. As we want to actually reuse some of those informations in here. But yeah, let's see what we are essentially now going to do here. So let's clean this up a little bit. We don't need this ray origin anymore. We don't need this wall position, wall size, canvas size. No, we don't need those anymore. Material, we might need some material. Let's see. We might need some light. We might need, or we will need, most likely, yeah, we will need a canvas mutex because we are still doing this in parallel. So yeah, let's maybe go ahead and have some basic parameters here. Like we want now a canvas width 7680, and this is actually the height. So the height is actually 4321. So yeah, so this would be let's comment this 8K resolution. So now we have this one, and this is actually then here the amount of lines we are tracing is the canvas height. The amount of rays we are tracing is canvas height by canvas width. No, let's do width here and height here, because why not? So yes, we need different spheres and different materials, but for now we are essentially really needing one light. So let's take this light here, as our world only supports one light for now, really. So let's get this light and let's define it in a way we like for our world. So yeah, I guess it can stay at -10, 10, -10. Why not? It's just right up there, nice and bright, and it's a bright, simple white light. Yeah, why not? Okay, so we will position this one there. And then we want 3 different spheres with 3 different materials. So let's define those quickly. And yeah, let me quickly define those, and then I will talk about what they are. So there we are. We have a left sphere, middle sphere, and a right sphere, all together with their corresponding materials, which all have a different color, a little bit different font settings here, which we might tinker with later on to see how they behave differently then, and corresponding translations and scaling. So the left sphere, for example, is a third in size and translated to this position, while the middle sphere has no scaling, therefore is a one-size sphere, and the right sphere is a half-size sphere scaled here, and all of those are translated somewhere in space to be simply positioned at a nice position there for us to see later on. So left, right, and in the middle. So yeah, so let's go on then, and after we have those informations here, we can further clean up our information. We now need a world, of course, which has all of those information together. So let's create one. We need to import one, of course, because we haven't done this yet. And then we are simply putting in, a vector of bodies, I guess. So we are putting in our left sphere, our middle sphere, no, not material, but sphere, and our right sphere. And then we need to put in a vector of lights, even though we only support one at the moment. So where's the problem here? Mismatch type, expected body. Yeah, we need to, of course, generalize those a little bit, because we have this thing implemented which will allow us in the future to have different types of objects there, and we have generalized all of this in the body enum and dispatching there. So now we have a world consisting of our 3 spheres and a light. So what is the next thing we need here? A camera, of course. So let's create one. So let camera camera new. We already have our canvas width and our canvas height here. And yeah, for our field of view, 90 degrees is a lot. So maybe 60 is quite okay. So P divided by 3 should be 60 degrees field of view. And we actually then want this one with, no, add from position. Shouldn't this work? Oh, we need to import the camera, of course. So now it should actually know this function. Yeah, it does. So now let's see. Let's look from. Where are we looking from? Maybe something like 0.0, 1.0, minus 5.0, something like this. Oh, no, this is not right. This should have been a tuple point, because all of this together is our from vector. And then maybe let's look at some point like 0.0, 1.0, 0.0. So we are looking on the x-axis a little bit up. We are not directly looking at the 0 position there. And the up vector then should be tuple vector. Let's just use the usual one just up the y-axis. So let's not rotate the camera here at all. So let's format this. And now we should actually have a camera pointing into the right direction. And now I guess we only need to, let's just create a let pixel count. Let's just have some pixel count here, which is canvas width multiplied with canvas height, because we need it at multiple positions. So let's use it here, and then let's use it here. Pixel count. So yeah, now let's see. We now have the x value, which is actually the canvas width. And we are creating those Cartesian product here with canvas height. And then we are iterating over all of this, and we can essentially more or less, I guess, remove all of this. Yeah, I guess we can. So for each something happens here, this can go away just to make sure. Yeah, we need to define this, of course. So now here we are getting the canvas, we are writing the pixel. This is something we won't change, but we need to change the calculation here. So yeah, let's do this. Usually this was within something else. Maybe we need this pattern matching again. Let's see. So what we can do now is we are getting a world, and we have our color add function, which actually takes a ray. And now we are just telling the camera to give us the ray for our pixel. And this should actually give us the color we want there. And this color can then be written into our canvas. And then we should actually be all right there. Of course, we need to fix up this here with canvas width. And no, not canvas. Canvas and canvas height, so that we are creating the correct canvas buffer. And now let's reformat this. And essentially, even though this is a little bit more code, because we are now creating a scene there, we may need to create something more easy. So from the syntax wise, we need something more easy in the future to define something like this. Our rendering itself now got very easy, because we have restructured things a lot and abstracted things a lot, and our work really pays dividends here, as we now can simply tell our world to give us the correctly shaded pixel for a specific ray, and we get this ray from our camera. So yeah, maybe we should check if this actually all works after fixing the unused imports, I guess. So this can go away, I guess, and we are not using illuminated anymore. That is actually right, because this is now used within the world color add implementation. So yeah, I guess we can give it a try now. Let's give it a try. Let's do what was it? Cargo run bin chapter 07 minus release. So let's see if this even compiles and then if it renders something. Yeah, release compiling takes a lot of time, and then yeah, there we are ray tracing, and yeah, we are ray tracing an 8K image with multiple spheres now in it, and yeah, it actually takes quite some time. Maybe we want to create a less big image, a little bit smaller one. Maybe 4K is enough. It's a fourth of the pixels. So yeah, there's actually our output. So the moment of truth. Let's see what we got there. And we got some output, and we have multiple spheres. And this is, let me resize this so that you can even really see it in its full glory. What you can see here now is we have non-square canvas, and we have multiple spheres, which are, you can see that they are differently positioned by the way they are lighted. So you can see that this one here, for example, is lighted differently than this one as with the shadow, because this seems to be on another Z position than this one. We defined it like this. So yeah, they are differently scaled. We have differently spheres. This is quite awesome. We have different colors here. Yeah, I really love it. It's awesome, and it's quite fast for that we just generated an 8K image, and it's not even really optimized. I'm still impressed how fast this is. So yeah, but in order to better see actually where the three-dimensionality of those spheres comes into play, I want to change some things around here, which the book actually tells us to do as well. And I will do something quite interesting now, because I want, in order to better see where they are positioned, I want walls. I want a floor, and I want a left and a right wall, which actually encompass this scene so that we can see this. And you might think, how is he going to do this if there actually is only a sphere he can render yet, and not something like we will of course render like planes and stuff like that in the future, but we can't now because we only have implemented a sphere yet. So what we are going to do here actually is a neat trick the book suggests. It's like, take a sphere for the walls, make it really big and squash it really flat by scaling it. And then you have a wall because it's actually looking the same. And this is what we are going to do now. So in addition to those spheres here, let's create our floor parts first. There we go. We are leaving it in the middle of the coordinate system, but we are scaling it in the X direction by 10 and in the Z direction by 10. We of course need to specify a .0 here. And then in the Y direction, so its height, it's squashed really, really tight. So what we have actually done is we have created a very large area in this direction and in this direction. So we have essentially our bottom base here, our floor, and we have squashed it tight together, so it essentially is still a sphere. If we would zoom out a lot, you would see its contour is a sphere, but it's quite big, and so it's just a bottom there, which we will then have. So this should actually work. So let's see if this works out later on. Let's copy this one because we need something nearly the same for the left wall. So what have we done here now? We have a matrix. We have, first of all, we are squashing this whole thing again. So remember, all those transformations always need to be read in the reverse order they are defined. So first of all, we are squashing this thing into the flat bottom and floor that we had before. Then we are rotating it by around the x-axis. So we are rotating it around the x-axis here by pi divided by 2, so by 90 degrees. So we essentially flipping it up, and then we are rotating it around the y-axis by minus pi divided by 4. So we are essentially putting it 45 degrees, like, wait a second, it's like this into space. So here's our floor, and we have now rotated it like this, 45 degrees. And the step we are doing the last is we are just moving it into the Z direction, so into the scene, so it's away from everything and in the background, and providing this wall there that we want on the left side. So essentially we are doing the same thing for the right. Now we have these spheres here, and now we just need to put our walls actually with everything else into the world. So let's add the floor sphere there, followed by the left wall sphere, followed by the right wall sphere. So now if we save this up, and maybe we can even change the colors a bit, because I guess the sphere colors should be more standing out. So like this. I might be horribly wrong with regards to this color. So let's run this one and let's see what the result will be. Yeah, so essentially adding those walls will be easier later on once we implemented planes and stuff like that apart from spheres, but we can simulate them with those squashed spheres there, and I guess it's going to look quite awesome, but we will see if I messed up the colors or not. So yeah, I quite messed up the colors. I didn't want those colors to be like this. But the end result, nevertheless, is quite nice. As you can now see, we have those actually shaded walls, and as they are, is there no specular part in them? They have just, as there is no specular part in them, they have just the ambient lighting and this direct shaded lighting, and therefore they are actually properly shaded here, and everything looks quite nice. And now you can see that those spheres are really positioned in three-dimensional space and are really here standing on this surface, and that is really nice. So let's quickly fix up those colors of those spheres, I guess, because I want them to be other colors, and then yeah, we have quite achieved something here. It's rendering, but hopefully we have a great result. So let's see, open, and that's kind of nice. I would have expected more shininess here, but maybe we need to experiment with it more. The orange one actually now is very not shiny as we have wanted it. This one here is quite shiny, and this is quite shiny as well, but maybe we don't even want it this shiny. So let's maybe make this one use just the default, I guess. Let's see. So yeah, why not? And maybe this one as well, because I guess the default looked quite nice, and we could actually dim the walls a bit more, like make them not this bright. So let's make them a little bit darker. So let's see how this actually turns out, and let me reduce the size here by simply putting in. Okay, so 3840, and we want a 180 times 2, so 216 here. So now we have a 4K resolution, which is a fourth of the pixels, and it should render a lot faster, and it should be enough anyways. Nevertheless, so this is the old one and this is the new one. Yeah, the background is a lot darker, therefore the spheres are a lot more shiny here, and yeah, I really much like this as an end result of this session. It's really nice. We now can render a world. We can have multiple spheres in the scene. We can transform them. We can position the camera. Maybe we could look at those things for once by changing the camera a little bit by, for example, where's our camera? Putting the camera higher. We could, for example, put the camera a lot higher and therefore changing the angle there it looks onto the scene. So let's see how this turns out then. I've just moved it quite a lot. So let's see. Yeah, and as you can see now, I've just moved the camera up by a lot, and therefore the angle is quite different. We are now looking at those spheres. I could even now change the, for example, let's change the field of view. Let's make the field of view a lot narrower. So maybe let's go from 60 degrees to 30 degrees. That would result in some sort of zoom-like effect. So let's see how this. So yeah, open this up again, and as you can see now, we have zoomed in on what we have seen before. Let me make this a little bit smaller. So we have zoomed in on what we have seen before quite a lot by just changing the field of view, and yeah, this is actually really nice. So let's maybe do this. Do not move this high, but for example, we could change the up vector. So let's maybe change the up vector a little and therefore rotate the camera. This should be quite interesting, as now the floor is not the floor anymore, as we have rotated the camera. So let's see. Yeah, and as you can see, it looks all oh no, I need to resize it because yeah. Come on, resize. Yeah, and now as you can see, this whole thing is kind of skewed because I've rotated the up position of the camera, and therefore it's looking into another direction, and this is quite obviously kind of seeming to be wrong because everything is tilted now. But yeah, it is what we told the system to render. So maybe let's do this one time again without this rotation problem thingy here. So yeah, let's see. So no, give me this one and make it smaller. Yeah. So yeah, so actually this is our scene and the end of this session, and I really love it because now we have all the possibilities to go further from here. We have now a fully functional world definition, a fully functional camera definition, which allows us to define a scene, to do all kinds of funny stuff in the future with it, and to somehow work with it, to position a camera, to position lighting and stuff like this, and just take a look at how this then works out to be a rendered image as a result. So thanks for joining me again for this session and for staying with me while we implement this Raytracer and while I learn Rust. I might refactor some parts with this builder technique I showed you, for example, like the materials and so on. I might do this off camera. But of course, I will give you a summary once it is finished. Yeah, thanks for joining me again on this ride, and I would be happy if you would join me the next time as well when we have the next session. So please subscribe if you want to be informed about new videos in this series and other videos I'm going to do in the future. Please give this video a thumbs up if you liked it, because this really makes a difference in people finding this kind of videos on YouTube, and it gives me some feedback that you like what I am doing here. So please give it a thumbs up. Please subscribe if you want. Leave me a comment, and I will go there and answer it if you have any questions or have any remarks. So thanks again for joining me, and the next time we will add some shadows to this, because where is it again? I had it here. Because this looks quite nice now, but you can't really see where those objects are. For example, this orange cube here, this orange sphere here could be floating up in the air. We don't actually know. It's either it's a little bit back here, back on the Z plane, or it is actually floating in the air and we can see it. And therefore we are going to add shadows in the next episode. So yeah, you can already prepare for that, and we will then add those shadows there and go along from there. So thanks for joining me implementing Chapter 7 of the Raytracer Challenge by James Buck, and I wish you a good time. Bye!